Okay, so we talk about some randomness properties, then talk about some standards. So let's look at actually some mathematical definitions and see what we can say if a sequence looks random or not. So let me give a few definitions. I will talk about Golomb's randomness postulates, by the way. So in order to give postulates, I have to give some definitions. Let's talk about run. A run in a binary sequence is defined as a set of consecutive zeros or ones. So for instance, there's a run of 4 zeros here, and there's a run of 6 ones here. Autocorrelation. Let A be a sequence like bits A0 to AN-1, n-bit sequence. Let this be a binary sequence of length n. Autocorrelation Ci of A is defined as A XORed with A rotated I bits. Okay, so you're actually XORing something this but rotated. So this way you look at it how related to itself. Okay, this is called autocorrelation. And there's an autocorrelation function, and you do it for every I actually. So autocorrelation function theta of a binary sequence is defined as follows: 1 over p multiplied by p minus 1, and is running from 0 to p minus 1, and an XOR an plus tau. Okay, so tau is a phase shift of the sequence an, and theta measures the amount of similarity between the sequence and its phase shift. So you're checking if you rotate something, how similar it will be to the initial sequence. So again, I'm giving these definitions because in Golomb's postulate we will use those definitions. So let's talk about pseudo-randomness. Only infinite length sequences can be random, okay? Because when we talk about random, this is what we define. Actually, this is also the thing. I mean, if you flip a coin 100 times, we would expect 50 many, tails and heads, right? But this generally doesn't happen. I mean, this has an expected value of like this. But when you did, maybe you will see 55 heads and 45 tails and so on. But the thing is that if you flip it infinitely many times, half of them will be heads. This is actually the definition of probability. This is the limit version of definition of probability. So we call a finite length sequence pseudo-random if it looks random. So question, how can we be sure that it looks random? So we cannot do it by human eye, right? We have to have some formula. So Golomb's randomness postulate is a nice one here. It says that number of ones and zeros should differ by at most 1. So this means that if it is even number of bits, number of zeros and ones should be identical, or if it is odd numbered, then the difference should be at most 1. So it also says that half of the runs should have length 1, and remaining half, which is 1/4 of the runs, should have length 2, 1/8 of the runs should have length 3, and so on. I will give an example to this. An autocorrelation function should be 2-valued. These 3 are the randomness postulates of Golomb. So let's apply it to a sequence and see if this is the case. So I chose 7-bit sequence like this. So there are 4 zeros, 3 ones. As you can see, the difference is at most 1. So it passes the first Golomb postulate, okay? So in terms of Golomb's postulate, this is random with respect to this property. So satisfies the first postulate. Let's look at the second postulate. So we divide it into runs. As you can see, there are runs of zeros here, then 1, a single 1, a single 0, then 2 ones. So we have 4 runs. Half of them has length 1, right? 1/4 of them has length 2. And 1/8 of them, but there are like 1, 2, 3, 4 runs. And if you divide it by 8, it will be 0.5, but it's still 1. So it has 1. There are 1 of length 3. So we also say that this satisfies the second postulate. So this is also important. For instance, if the sequence will be a lot larger, we will see a huge run, like 8 zeros or 8 ones, right? Due to this postulate. But this is counterintuitive for humans. For instance, this is actually how I can check if it's something generated by a human or not. And this is actually done by instructors many times. I don't have the time, but I could ask you to, generate random zeros and ones. Write zeros and ones, for instance, at length 30 on a piece of paper. So you will write zeros and ones by your choice. But then I will also, some of them will be generated with a random number generator. You will give it to me and ask me if it is generated by a random number generator or it is generated by you, a human. And I will most definitely detect correctly because I will look at the longest run. And if it is generated by humans, humans generally don't write more than 3 or 4 consecutive bits. But the computer will generate like 5 or 6 consecutive zeros, which will pass this postulate. So, but humans will not be able to pass this postulate, okay? So this is an easy way to detect if it is random or not, okay? Third one is, what you do is as follows. These are the phase shifts. So your sequence is S. You rotate it 0 times, so it is identical to itself. You XOR it, so the result is 0. So the C tau will be 0 divided by 7. So if you rotate it 1, this will be XORed with this. The result will be this. So you perform this formula here. Let me go back this. Okay. You're actually counting, once and then divide it to the number of bits actually. So you do it and you realize that the result either 0 here or 4 over 7 here. So it is 2 valued, so it passes the third postulate too. Okay, so this is how the Golomb's postulates work. So these are the ideas, because this is what you expect from a random number. Okay. Okay. Sorry for that. So these are just postulates telling you what we would expect from a random number. Okay. So we can use these ideas and then generate statistical tests to measure if something looks random or not. Okay. So various statistical tests can be applied to a sequence to attempt to compare and evaluate the sequence to a truly random sequence. Randomness is a probabilistic property. That is, the properties of a random sequence can be characterized and described in terms of probability. So NIST has many actually documents and tests. One of them is for entropy sources. Okay. So for instance, this publication first performs health tests. This actually is done by running the device many times and see if it is working properly. Then test the independence assumption, independently identical distributed assumption. There are 11 tests. Then estimates minimum entropy with these tests. And if it is high, it says that your entropy source looks like producing high entropy. Okay. This is entropy test, not randomness test. But if your random entropy source is nice, then you use this information to produce random numbers. So in that scenario, just by looking at the zeros and ones you produce, you perform this test suite generated by NIST, again with a publication with this number. And in this test suite, there are many tests, and you put your input and check if your sequence passes this test. Okay, for instance, in the frequency test, it actually uses Golomb's first postulate. So you give for instance, 1 billion zeros and ones, a sequence. It doesn't check the ordering. It just checks how many zeros are there and how many ones are there. And by looking at the difference, it checks if that difference is small within, acceptable error rate. So you actually choose a p-value. This is what it does. So if you pass this test, this means that your number of zeros and ones you generate actually close to each other. But of course, this is not enough, right? For instance, if I generate 100 bits, where first 50 bits is 1, and the remaining 50 bits is 0, it passes this test, but it doesn't look random, right? So you have to perform other tests, like the runs test uses the Golomb second postulate, but there are many different tests. So if it passes these tests, you say that this sequence looks random. So this is how you actually should evaluate your random number generator. Again, passing this test doesn't mean that your random number generator is secure or produces random numbers. because remember my examples. Take a yes, choose a secret key, run it in the counter mode. The outputs you will get will pass all of these tests. Okay. So passing this test doesn't mean that your random number generator doesn't have a backdoor. Okay. It only says that the output looks random. That's it. Okay. So there are other test suites too, like Cryptics, Die Hard, Die Harder, Test Use 01. Also in our university, we had many times developed our own test suite called Sadist, and actually has a lot more tests than compared to these test suites.